In this video, we're going to look at more questions on pulleys. Let's take an example. Two particles A and B have mass 0.4 kg and 0.3 kg respectively. The particles are attached to the ends of a light inextensible string. The string passes over a small smooth pulley which is fixed above a horizontal floor. Both particles are held with the string taut at a height of 1 meter above the floor as shown in figure 3. The particles are released from rest and in subsequent motion B does not reach the pulley. Find the tension in the string after the particles are released, and hence find the acceleration of A immediately after the particles are released. So I've drawn all my forces onto my diagram with the direction of acceleration as well. So the first thing we ought to do is to resolve. So let's do particle B first, as that's going upwards. So we're going to resolve vertically. So it's going to be T minus 0.3 G equals to 0.3 A. Then for particle A, it's going downwards, so we're going to resolve downwards. So we're going to say 0.4 G minus the tension equals 0.4 A. Standard simultaneous equation, add them together, so we get 0.1 G equals to 0.7 A. So A equals 0.1 G over 0.7. So A is going to be 1 over 7 G meters per second squared. Now to find the tension, we're just going to substitute. So T minus 0.3 G equals 0.3 A. So T minus 0.3 G equals 0.3 times 1 over 7 G. So T equals to 0.3 G plus 0.3 G over 7. So I'm going to leave my answer in terms of G. So I'm just going to do the following on my calculator. 0.3 plus 0.3 over 7 plus equals. Now part C is very important. It says when the particles have been moving for 0.5 seconds, the string breaks. Find the further time that elapses until B hits the floor. So we need to understand what's going on here. So B is moving and it travels some distance for the time period when T equals 0.5. So we need to work out what is this distance travelled by B. That's the first point. Then at this point, the string breaks. So tension is no longer there anymore. The particle is now moving freely under gravity at this point. It moves a little bit further up till it reaches a maximum height when V equals 0. And we also need to know what is that distance. Then what happens is when it reaches the maximum height, it drops all the way down to the ground again, particle B. So in a nutshell, this is what we're looking at. So let's first of all work out the distance travelled by B in the first 0.5 seconds. So we're going to do that by SUVAT. So this part is the distance travelled by B in the first 0.5 seconds. Okay, so we said that we're going to do that by SUVAT. So we're going to do a SUVAT here, and we're going to use A equals 1 over 7G. It starts from rest. We're trying to work out the displacement in that time, and the time is 0.5 seconds. So we're going to use S equals ut plus a half at squared. So S or U is 0 plus a half times 1 over 7 g times a half squared. So on my calculator, I can do 0.5 squared times 0.5 times 1 over 7. Again, I'm going to leave it in terms of g, so I get 1 over 56. So that's 1 over 56g. So that's the distance travelled by B in the first 0.5 seconds. Then if you go back to our diagram, we also need to work out the distance travelled when it's moving freely under gravity to maximum height when the string breaks. So I'm going to say when the string breaks, this is the distance to maximum height. This is the distance to maximum height by B. Again, we're going to use SUVAT. And it's particle B we're talking about here. Okay, we're taking upwards as positive. So we know that it goes to maximum height. It's traveling under gravity, so it's minus g. We're trying to work out the displacement, but we need to know what the final velocity of A is. So let's do that for A. Taking down as positive, let's do a SUVAT. Here we're going to work out the final velocity of A. So we know that the acceleration was 1 over 7g. It starts from rest. We're trying to work out what this velocity was, and it took 0.5 seconds. So we're going to use v equals u plus at. So v equals to u plus at here. So we can say v equals to 0 plus 1 over 7g times a half. So we can say that v was 1 over 14g. 1 over 14g. Now the final velocity of A will now become the initial velocity of B. So we can plug that in here. So this is 1 over 14g. Now we're trying to work out the distance to maximum height when the string breaks. So I'm going to use v squared is equal to u squared plus 2as. So let's substitute this into our SUVAT equation. So we've got 0 squared is equal to 1 over 14g all squared minus 2gs. So 2gs is equal to 1 over 14g all squared. So we can then say that s is 1 over 14 g all squared divided by 2g. Let's work that out as a decimal here. So we're just going to say that we've got the following: 1 over 14 times 9.8 squared divided by 19.6. And that gives me 0.025. 0.025 meters. So what that basically means is that we've now got the total distance now from the ground all the way to maximum height. So I'm going to say that the distance from the ground to the maximum height. So you've got to be careful in the addition here. So we know it's already 1 meter above the ground. Then it travels a distance we worked out of 1 over 56g. So we need to add that, 1 over 56g plus the distance when the string breaks to maximum height, which is 0.025. Now we can work this out on our calculator to give me 0.025 plus 1 over 56 times 9.8. And that'll give me 1.2 meters. So what happens when B falls downwards, if you go back to our diagram here, it falls from the maximum height down by a distance of 1.2, and B is going downwards. So we're going to do SUVAT for that. So we're going to find the time for that. So from max height to the ground. So for particle B, taken downwards is positive. In the SUVAT again. And it starts from rest. Displacement's 1.2 meters. It's moving freely under gravity, so it's going to move. It's going down, so it's G, and we're trying to find the time taken for that. So now what we're going to do is S equals to UT plus a half AT squared. So we're going to have 1.2 equals to 0 plus a half times G times T squared. So 1.2 equals to 4.9 T squared. And then we're going to do T squared equals 1.2 over 4.9. T squared is equal to 1.2 divided by 4.9, which is 12 over 49. Square root that. So T equals to the square root of 12 over 49. So T equals to the square root of that, which is 2 root 3 over 7. Now we also need to do another SUVAT here to find out the time to maximum height for B. So let's do a SUVAT here. Now it's minus G goes to maximum height. We said that the final velocity of A will now become the initial velocity of B, and we need to work out the time. So we're going to say V equals to U plus AT, 0 equals to 1 over 14G minus GT, GT equals to 1 over 14G, so we've got T equals to 1 over 14. Now for the further time elapsed, we know that the time to maximum height when the string breaks is 1 over 14, and we also know that the time from maximum height going down to the ground is 2 root 3 over 7. Now we can do this on our calculator. So plus 1 over 14, and that will give me 0.563 and so on. So we can round that up to 0.57 seconds. Here's a question for you to try. You can pause the video, and when you're done, I will go through my work solution. Okay, welcome back. So we've got two particles A and B of masses 2m and 3m respectively. The particles are connected by a light inextensible string which passes over a smooth light fixed pulley. The system is held at rest with the string taut. The hanging parts of the string are vertical, and A and B are above the horizontal plane, as shown in figure 2. The system is released from rest. Show that the tension in the string immediately after the particles are released is 12 over 5 mg. So the first thing we ought to do is to draw all our forces. So we've got the weight coming down, 2 mg, weight coming down from this particle, 3 mg. We've got our tensions for each particle respectively. We need to include the acceleration. So A is lighter, so it's going to be A going this way, and then we've got A going this way. Now we're in a position to resolve. So we're going to resolve vertically for particle A. So T minus 2 mg equals 2 ma. For B, we're going to resolve downwards. So that's 3 mg minus T equals to 3 ma. Simultaneous equation, add them together, so we get 3 mg minus 2 mg is mg. The tensions cancel out, and we get 5 ma. The m's cancel, so therefore a is a fifth of g meters per second squared. Now we want to show that the tension is 12 of 5 mg, so it's T minus 2 mg equals to 2m times a fifth of g. That gives me T minus 2 mg equals to 2 mg over 5. So T is 2 mg plus 2 mg over 5. We're going to add them, so don't forget this is over 1. So times this by 5, times that by 5. So we end up with T equals 10 mg over 5 plus 2 mg over 5, so T, and that's exactly what they want us to show. Then part C says, after descending 1.5 meters, B strikes the plane and is immediately brought to rest. In the subsequent motion, A does not reach the pulley. Find the distance travelled by A between the instant when B strikes the ground and the instant when the string next becomes taut. So if we look at our diagram, what's going to happen is B is going to go down to the ground. A carries on moving up slightly more to maximum height, and then it moves back down again until the tension resumes or comes back. So let's draw a diagram so we can visualize that, what's going on. So here's the ground. B hits the ground, and then what happens is, here's A. Then what happens is, I'm going to draw this in pink. So A is going to carry on moving to some maximum height there. Let's call it the maximum height. And then don't forget, at this point the string's broken, so it's going to move under gravity, so minus g. It's moving upwards. And then what happens? Then once it gets to maximum height, it's going to come back to this point, and at this point the tension is resumed, or it comes back again. So that's basically our model. So we can tell originally that B was going down, so we want to find the final velocity as B hits the ground. So we can do a see that here. So we know it starts from rest. A was a fifth of g. We don't know what the final velocity was, and we know that S was 1.5, and we'll just double check that in the question here. Yep, after descending 1.5 meters. So now we're going to use, for particle B, v squared equals to u squared plus 2as. Then we can say that v is 0 squared plus 2 times a fifth of g times 1.5. So that will work out to be v equals the following. So we get 3/5 of g, and don't forget this is v squared, so v is going to be the square root of all of that. So v is the square root of 3/5 of g. So this is the final velocity of B as it hits the ground. So now what we're going to do is we're going to find the distance from when the string breaks to maximum height that A travels, this pink part here. Okay, so that's going to be the distance when the string breaks to maximum height. So we can say for particle A, it's going upwards. So let's just do that now. So be careful that u is now going to be the final velocity of b, which was going to be the square root of 3/5 of g. It's moving freely under gravity, so a is minus g. We want to work out s, and it goes to maximum height, so v is 0. So now we can go ahead and use SUVAT. So we're going to use v squared is equal to u squared plus 2as. So v is 0, so we get 0 squared. U squared is just 3/5 of g, because the square root and the square cancel out, minus 2gs. So we get 2gs is equal to 3/5 of g. The g's cancel out, so I simply get 2s is 3/5. So s is just 3/10. But meters. But what we need to realize is from the time the string breaks, that distance to the maximum height is 3/10. But it travels 3/10 from the time the string breaks to the maximum height, and back down the same distance to come back to the position which is in blue when the tension is resumed. So it's 3/10 plus another 3/10. So that's why we double the distance. So the distance required. So the distance required is 3/10 plus another 3/10, which gives me 6/10 meters, or we could write 0.6 meters.